It was pretty ruthless, and a lot of things that Edison did was, I don't know, it's questionable.
Didn't he kill like animals in a park?
He did. I think he
I heard
tried
about that.
elephant actually. And he also, I don't know if you guys are aware of, Edison invented the
Oh my
electric
God.
chair for executing prisoners. And of course, he used AC for that. So that was a little extreme. But keep in mind too, Edison was really a salesman, businessman type slash technician, where Tesla was a physicist slash engineer. They were really very different people, but it was I don't know. This is interesting history of some of the people back in the day, and that was a little extreme, I thought, in my case. But Edison, he did contribute a lot to all the inventions, some of which that we're using now. All right, I'm sorry. I a couple more problems to go. Something we've done recently, we have a motor that contains a coil of total resistance of 1.5 ohms and a current of 2 amps flows through the coil the instant power is supplied to this motor. And when the motor is running at its maximum speed, the current is dropped to 1.4 amps. And then the question is, well, of course, we're going to talk about the back EMF as a result of this. But we want to find the voltage across the coil at the instant the motor is turned on. Okay, and at a given time, 2 amps flows through the coil. And we have a 1.5 ohms. So this is a pretty straightforward part. So we have 3 volts across the coil. But after the coil is rotating, when it reaches its maximum rotational speed, it's down to like 1.4 amps. It's gone from 2 to 1.4. As a result of the back EMF that's been produced in the coil, as a result of this coil rotating in and out of this magnetic field that's produced. And the way we do this basically is just take the difference between the current when the motor is stationary, when it's turned on, and that when it reaches its maximum speed times the resistance. That gives you the back EMF. Not something you can measure directly. It just can be implied by taking the differences of what's being observed during the stationary and dynamical case. And from this is 0.9 amps. Actually, we did a demonstration on this, I believe, a long time ago. All right, so the back EMF is 0.9. All right, and try to get this last one. Let's see, how much time do I have? Oh, I've got 4 minutes. Let's see, which one is this one? Okay, yeah. So let's consider our uniform wound solenoid have an end turn. L is much longer than the radius of the winding, so we can just ignore the fringe effects at the ends. And the core of the solenoid is air. So mu is mu naught. And the question is, what is the inductance of the solenoid? Definition of self-inductance, number of windings of whatever coil are being considered. It's the magnetic by I, no current I. So in the solenoid, magnetic flux, phi equals BA, B being the magnetic field inside the coil, into the solenoid, in the cross-sectional area of the solenoid. Okay, so Remember, he's using amperes to do this type of problem. And lines is uniform inside axis of the solenoid. On the outside, the path from C to D, we're assuming the magnetic field is very small or zero. It's not really zero, but it's just very small, at least in comparison to that inside. And of course, the magnetic field doesn't, I mean, the BDS, DS is in a vertical direction. Is perpendicular to that. So it does not contribute to this integral. So it's really only this path from A to B that contributes to this closed path integral, B dot ds. And this is my little L. It doesn't quite distinguish some of the other, but this big L is the same as my little L here. So BL equals mu naught N is I. Okay. And keep in mind this N here is the N, it's the number of windings that are enclosed. These out here do not count. So this is here, and this is 1, 2, 3, 4, 5, 6, 7, 8. So N in this case is 8. So this is, you just have to multiply that. This said we're closing the current many times as it wraps around. Alrighty, and so now we can solve for the magnetic field for the solenoid based on the current. Alrighty. So substituting this back into this equation, flux. What we do here is just substituting for B for the solenoid magnetic field. And that's where we get this relationship here. We have an N squared as a result of this enclosure of the N many times. All right. So now the question is, we have this relationship. We want to calculate the inductance of the solenoid if it contains 300 turns and its length is 25 centimeters. Okay, and so this cross-sectional area is 4 centimeters squared. We have all these values available to us, so it's just a matter of just substituting these guys in. Okay, this is our epsilon, our mu naught. Total number of turns, within this region L. Okay. So in other words, it's important to note that you wouldn't use the total number of turns if your L is less than the total length of the solenoid. It's only that part in which this is like the number of turns within length L is what this N value is, just to make that clear. All right, so making these substituting in these values, 300 turns, 0.25 centimeters, and we had to convert this to meters squared, so we had to divide this by 100 twice, right? So that's where you get this term here, -4, and as a result, we get 1.81 times 10 to the -4 henries. Oh, I'm already over, so let's finish this last part very quickly. So we want to calculate the self EMF in the solenoid. The current is carrying decreases at a rate of 50 amps per second. And this is Faraday's law, at least in the form of using self-inductance. And all this is given to us. We have the inductance for the solenoid. The IDT is given to us explicitly. So we just substitute the answer. So it's 9.05 millivolts in this case. Actually, not very high. And sorry, as usual, fashionably late, keeping you over once again. This is it. This is all I have to show for the review. I can stick around for some questions if there are any.
I just had a quick
The
question
final-
with.
Oh, sorry.
Go ahead. You're good.
Oh, is the final cumulative?
Well,
I believe you mentioned that it
yeah,
was.
I said early, there's 6 problems, right? And 4 of those 6 will come from the material that we covered since the last midterm. And then 2 of those problems will come from the other material prior to that. And for the most part, you could use the exams 1 and 2. Those 2 problems will not come directly from those 2 exams, but it'll be very close, I would say. There may be some combination of the 2 of the problems, but yeah, there'll be one of the 2 will come from the first exam material, and the other one will come from the midterm exam material.
Are we allowed to have a cheat sheet or just the provided
cheat
formula
sheet.
sheet?
Just
Gotcha.
no, you should never be using a cheat sheet. You don't cheat in this class. We have a reference sheet, and that's, I assume that you got that from for the last exam, right?
Yes, I still have it.
Yeah. I mean, that's this is pretty much like a standard midterm. I mean, same rules, same protocol format. It's just that you'll have an extra 2 problems, and you have 2 hours as opposed to 1. But yeah, I mean, that's okay. And I'll send around an email, stating a little bit more. But I mean, like I said, it's just like it'll be very similar to the previous midterms that we had.
Thank you.
Yeah, you're welcome.
Can we go back to question 3 for a second?
Oh, 3?
Yeah.
Sure.
Thank you, Professor.
What's that?
I said thank you.
Oh, sure. Oh, this one.
Yes.
Yeah.
I just wanted to review this one. I mean, just to view this one because I was not done.
Oh,
And maybe question 5.
let's see if I can.
You're posting these on Canvas, right?
I can't really hear very well. I mean, so what was the? There was something about this problem, or you want me just to go over it again? Is that it?
No, I just wanted to write down there was something that I needed to write down from